Welcome to the presentation of this scientific paper, and the title of this paper is Short-Term Kinetic Energy Forecast Using a Structural Time Series Model, a study case of the Nordic Power System. This paper is the collaboration between Marta Noemi Acosta from University of Nuevo León and also from University of Southeastern Norway, Harold Chamorro for KU Leuven, Daniel Top from University of CIGEC, and myself, Professor Francisco Gonzalez from University of Southeastern Norway. And let's start. Um, This total system inertia in a power system is an extremely good indicator about the robustness of the power system, especially when we are talking about frequency control and frequency stability. The total kinetic energy defines the capability of the power system to survive to a power imbalance, a difference between generation and demand. However, today we have a high penetration of power electronic based technologies like photovoltaic system, wind power, HVDC, and so on. What is creating is the generation mix is changing, but also the number of classical synchronous generator connected into the system is reducing. Of course, one of the key elements of this reduction on the number of classical synchronous generator is the reduction on the real physical rotating inertia. As a consequence, for many years, transmission system operators around the world has been interested on having a full knowledge about the total system inertia. And the Nordic Power System is one of the if one of the set of this TSO that is interesting on that, because it's expected that the future scenarios, the increased integration of wind power and the decommissioning of several nuclear power plants in the Nordic power system will create a problem of system inertia reduction. Also, the target of increasing 50% of the capability between interconnectors in the Nordic power system is also another issue that is creating a system inertia. It's estimated for the Nordic power system that the total kinetic energy will be reduced to 120, 125 gigawatt seconds for periods in the future years. For that reason, this paper presents the result of a short-term forecast algorithm that is called a structural time series model. And the idea of this paper is to show you the basic results of the short-term kinetic energy. And we are using in this paper kinetic energy instead of the rotational inertia. And one of the reasons is that the kinetic energy is basically the physical quantity that is giving you the total capacity of the system of surviving at the frequency event. And also, using kinetic energy, we avoid the issue of referring the inertia to a very specific base. And also, there are already some recording devices and measurements inside the Nordic Power System collecting the data of the kinetic energy. That make easier for us getting access to the information. Making those considerations, we are using only the system kinetic energy as the variable that we want to forecast. But before we go for results, we need to define some basic terminology. A time series is just a set of data points indexes over the time. That is basically a time series. And the time series are quite good in order to be used for representing a stochastic process. And the idea of this paper is that we are using a mathematic tool in order to forecast a time series. And to be honest, when we have time series forecasting, is extremely simple because you want to estimate the value of the time series over a time horizon. Um, If you have information about the time series, you can select better the method that you can use for using the time series. Investigation in time series has been divided historically into main areas. One is descriptive modeling, and the idea is to get information how to describe the model that is represented by the time series. And the second set of investigation of time series is predicting, modeling, or forecasting. We will focus in the area of forecasting, and four broad categories are defined. One of them is the use of the composition-based method, smoothing-based method, regression-based method, and machine learning-based method. This one is quite brand new and is showing very interesting result. However, in this paper, we are using time series forecasting using a very specific model that I will discuss in a few minutes. But what you need to do is that the process for forecasting have basically several steps: problem definition, data collection, data analysis, model selection and fitting, model validation, forecasting model development, and finally monitoring the forecasting model performance. This is the whole process of forecasting. However, this paper is only focusing on the first part, and that is modeling, selection, and fitting. Then we will go for the forecasting model, and the forecasting model that we are using here is something called this decomposable time series model. Decomposable time series model say that the time series must be decomposable in several components. One of them is related with the trends of the time series. The other one is trying to identify and model periodic changes related with seasonality mainly. Then we have a component to represent irregular changes, or changes that cannot be easily found in the other two categories. And finally, we have um, some, let's say, idiosyncratic change that is not included in the model. What I'm trying to tell you is that the decomposable time series model is basically this equation over here that have the four different components that we have explained here. The next step is define each one of those components, and let's start with the trend model. The trend model is trying to identify basically tendencies that we have inside the time series. And for that reason, in this paper, we have include two different trends model. One is the nonlinear saturating growth model, and that is represented basically using a logistic growth model. Here, this is the equation representing the logistic growth model, and these coefficients inside the model are defined below. The second component that we consider here for the trend model is a piecewise linear model. In this case, if we have very specific data about some special seasonal performance, we are able to include those events, those tendencies using the PWL model. Then we have here the two last components, and as you can see over here, the seasonality model can be represented by using the classical Fourier series to approximate the smooth seasonal effects. And over here you can see the classical Fourier decomposition. And finally, for the irregular component, we are using the regular component of a time series, and the function that is used to represent is basically a combination of components, and it is represented by these irregular changes using this function over here. Now we are going for experimental results, and what you need to know is that we are using the historical data of the kinetic energy that has been recorded in the Nordic Power System. Yes, the Nordic Power System has been recording the total kinetic energy in the system, and we took the data, the time series from January 2018. The raw data of the time series has a resolution of sample per minute, and that means that we are using 44,640 points. The kinetic energy in that period is changing between 172 to 268 watt seconds during the month of January 2018, and the standard deviation was around 22.99 gigawatts seconds. Over here you have a classical plot, and you can show and you can see the total time series for the whole January 2018. And below, what I'm showing here is a histogram showing the cones, and the horizontal axis is the total kinetic energy. As I say before, the kinetic energy is going from 268 gigawatt seconds up to 173 gigawatt seconds. Now the next step is the fitting of the model in, and for that process, what we are using is finding the point estimate by maximizing the joint posterior from the model. And in this case, we are using limited memory Broyden, Fletcher, Goldfarb, Sahano algorithm. The small name is BFGS algorithm. The training set consists of 1,440 samples, and that is the recording of one day, 24 hours on 31st of January 2018. And then the data set is used containing the other 30 days of January with a 1 minute resolution. That means 43,200 records. The target is to forecast 24-hour using 1 minute resolution. Over here you can see the numerical result. This plot over here shows the total time series. In this case you have the full month, and over here you can see how good is the relationship between the tendency that it was recorded by the model and the actual data. Here we have different trends. We have the trends, the weekly, and the daily behavior. However, what is important here is using some index to define the performance of the model. And in this case, we are using the cross-validation procedure in order to measure the forecast error using the historical data. In this case, the cross-validation is based using the forecasting horizon of 24 hours with one sample per minute. And then what we are doing is basically calculating a measurement indicator, and in this case we are calculating the mean absolute percentage error, that is called MAPE. And this is basically an indicator that allow you to define the prediction accuracy of the forecasting method. Over here we have two plots. One of them is basically the MAPE over the 24 hours, and as you can see over here is below 6%. And the other indicator that we use in this paper to examine, to see the performance of the forecasting method, it was the RMSE. In this case, as you can see, depending of the time during the 24-hour period, you can see how the error is below, in some cases below 20%. Okay. And here, what is the conclusion of this paper? Well, the conclusion is that we present here a mechanism that is allowing you to forecast the kinetic energy using what we call the decomposable time series model. This is a very important step forward because we are looking into some mechanism for estimating inertia in real time, but also Estimating inertia in real time is not good enough. Right now, if the inertia keep reducing, we need to take actions in a very clever way, and predicting inertia and using predictive controllers, that is one step forward that we are working for. Finally, I would like to say that we use the kinetic energy of the Nordic Power System, and we tested the decomposable time series model, and the cross-validation process revealed that the mean absolute value error, forecast error, it was below 5% into the predictions in 1 hour into the future. Well, this is all for this presentation. Thank you very much for watching this presentation, and we hope this will provide useful information for you. Thank you very much. It's time for question and answers.